Now let's assume this mass spring damper system, and as we can see, it's a 1 degree of freedom system, and it's a free vibration because there's no external force applied. So we are dealing with the initial excitation, and so we'll try to solve this system using both the general solution method and the Laplace transformation method, so that you can easily identify the difference between them and how much uh, less work you have to do in the Laplace transformation compared to the this general solution method. So let's assume that we have an initial condition for this one, that the displacement of this mass at time equals to 0 is equals to x naught, and the velocity of this system at time t equals to 0 is v naught. And assume some properties. Let's m mass equals to 10 kilograms. Stiffness for the spring 1 is 50 newtons per meter square, newton seconds per meter, and stiffness for the second damper is the damping for the second damper is 70 newton seconds per meter, and the stiffness for the first spring is equals to 400 newton per meter, and stiffness for the second spring is 600 newton per meter. So that's all we have, and now we'll start with the solution using the general solution method of a differential equation. So again, as we discussed earlier many times, so whenever you're dealing with a free vibration, just assume, decide yourself like which direction is positive. So let's say we said this is positive direction, it's positive x-axis, and our force was initial excitation was also given in the positive direction, and our system obviously naturally moves towards the positive direction. So this is what we have assumed in the beginning. So based on that, what kind of free body diagram we will have is, let's say this is our mass, so a system is moving in this towards a positive direction, so this spring 2 will be opposing the movement. Same is the case with the spring with the damper 2, they both will be pushing it backwards, while this spring will be pulling it backwards towards its initial position, and same the case with this damping force. You can use either Newton second law method or D'Alembert principle, both are similar. So let's assume that summation of all forces equals to mx double dot. So based on that, we can write it as mx double dot equals to minus of k1x minus of k2x minus b1x dot minus b2x dot, and we can write it as mx double dot equals to minus x into k1 plus k2 minus x dot into b1 plus b2. X dot means the first derivative of x, and we can rewrite our equation as mx double dot plus x dot b1 plus b2 plus x of k1 plus k2 whole equals to 0. So this is our general solution, the general equation of our system. And the second thing is we can linearize if we are using the general solution method. Using the general solution method instead of Laplace, we linearize our equation, divide whole by m, so it become mx double dot plus b1 plus b2 divided by m into x dot plus k1 plus k2 divided by m into x equals 0. So from here we know that natural frequency would be equals to under root of k1 plus k2 over m, and the damping coefficient, the twice of the damping coefficient, would be equals to b1 plus b2 divided by m. So from here we can find it out, the values of natural frequency and the damping coefficient. It becomes omega n equals to k1 plus k2, that's equals to 400 plus 600, so it becomes 1000 divided by mass 10 kilograms, it becomes 100, and under root of 100 is 10, so we have 10 is the natural frequency of our in our case. And here it becomes 50 plus 70 divide by 10, and it becomes 50 plus 70 is 120. 120 divided by 10 is 12, and so 2 into damping coefficient is equals to 12, and damping coefficient will be equals to 6. So these are our values, so we'll just put it aside so that we can use it later. Now using the general solution method of differential equation, where x is equals to ce exponent lambda t. I'm not going to repeat all those steps, you know very well, we have discussed this in the previous lecture. So if you have to take the single derivative, then take the double derivative of the same, and then substitute in this equation a, and after that you will have a trivial solution and you will have the non-trivial solution. So you will get, what you will get at the end is, your equation a will become lambda square plus b1 plus b2 divided by m into lambda plus k1 plus k2 divided by m into lambda equals to 0. So now our differential equation has been converted into the algebraic equation using this general solution method. And we know that the two roots, using the quadratic formula, it will be minus 2 damping coefficient plus minus under root 2 into damping coefficient square minus 4 into 1 into omega naught, that's or omega n you can say, square divided by 2. So if you solve these equations, what you will have, if you can just further simplify this one, it will become minus damping coefficient plus minus under root damping coefficient square minus omega n square, or you can write it as omega lambda 1 to the both roots will be equals to minus lambda. Just inverse this one, take out in the form of an iota, it become omega n square minus damping coefficient square. So it makes us minus 6. Let's substitute the values, plus minus iota, that's omega square is 100 because omega was 10, so it becomes 100 minus 36, and so 100 minus 36 is 64, under root of 64 is 8, so it becomes minus 6 plus minus 8 iota. That's our two roots of our system. So after that, we know the general solution, the total solution, would becomes, in the homogeneous cases, k1, or you can call it a1 or c1 or d1, whatever you want. It's just better to use any other one, just not mix up with the stiffness. Let's say a1 e exponent lambda 1 of t plus a2 e exponent lambda 2 of t, and you can start substituting the values of our roots. So a1 e exponent lambda 1 of t is minus 6 plus 8 iota into t plus a2 e exponent minus 6 minus 8 iota into t. And after that, you can take e exponent minus 60 as common, it becomes e exponent minus 6 t as common. Also you will have whatever left is a1 e exponent 8 iota t plus a2 e exponent minus 8 iota t. That's all for so this is what we have. And then you can use a Euler's formula to expand this further. So just define it in the form of sine and cosine instead of exponential functions. E exponent minus 6 of t, a1 and 8 iota t would be becomes cosine, it becomes cosine 8t plus iota sine 8 of t plus a2. Now this becomes cosine 8 of t minus of iota sine 8 of t. You know this Euler formula, so you can refer to the last lecture. We discussed this we briefly looked this one. So x of t would becomes, you can separate cosine and sine, e exponent minus 6 of t, so it becomes cosine of 8t into a1 plus a2 plus iota sine of 8t a1 minus a2. now we have separated the whole solution in terms of cosine and sines. So, and since a1 and a2 both itself is a constant value, so you can define by another constant value. I call it c1 and I am calling it c2. So x of t e exponent minus 60, just to reduce the calculation because they are constant. Their summation will also be a constant value. So it will be c1 cos of 8t plus c2 iota sine of 8t. Now we know that we had an initial condition which says x at 0 is equals to x naught and x dot of 0 is equals to v naught. So we have to take the derivative of this one. We can just substitute the first condition in our solution. So it will become x at t equals to 0. So x at 0 is equals to e exponent 0 or into c1 cosine cos 80, so it's become cosine of 0 plus c2 iota sine of 0. So sine 0 is 0, so it becomes 0 and this becomes 1. This becomes equal to 1. So we are left with x of 0 was equals to x naught and cos of 0 is 1, so c1 equals to x naught. So we now have found the one value of a constant. We can substitute the second initial condition. For that we have to integrate, or we have to differentiate this equation, call it equation b. So we have to take an integral of this one, so it becomes x dot of t. So that's right, we are taking d over dt of equation b. So it becomes x dot of t equals to a minus e exponent. I'm not going to follow all the steps and cos the integral of this cos of 80 would be the minus sine 80 into 8. So 8 sine of 80 plus cos of 80, sorry, into minus 6 into minus 60 plus, sorry, that would be c1 not a, plus c2. Now the second part is c2 iota sine 80. So we have to differentiate that one as well. So it will become, because we are multiplying e exponent 60 as well to both, that's why it's a multiplication rule of differential. So e exponent minus 60 into 8 into cos of 80 plus sine 80 minus 6 e exponent minus 60. So this is what we have after differentiating that one. In this equation you can substitute t equals to 0. So at, you can just zoom in, at x dot of 0 equals to v naught. So just substitute v naught equals to c1 minus e exponent 0, 8 into sine of 0 plus minus 6 into cosine of 0 into e exponent 0 plus c2 e exponent 0 into 8 cosine of 8 into t is 0 plus minus 6 into sine of 0 e exponent minus 6 or minus 0. I'm just maintaining the sign just not to confuse everything. So what we have at the end will be v naught equals to c1. So this expression is equals to 0. So we are left with minus 6. That's it. So you're left with minus 6 here and plus c2 what we are left with here is e exponent 0 is 1, 8 cos 0 is 1, this becomes 0, so we are left with 8. So our new equation is v naught equals to minus 6c1 plus 8c2, and from here what we got from the previous one, we had the value of c1, so we can substitute the values, we can find the values of c2. So since c1 is equals to x naught, so we can find v naught equals to minus 6 x naught plus 8 c2, and c2 would be equals to v naught plus 6 x naught divided by 8. So we have the value of c2 and we have the value of c1. You can substitute back these values into our equation b here. So now we have is x of t, c1 is x naught, so let's write e x60, c1 is x naught cos of 8t plus c2 is v naught plus 6 x naught divided by 8 into iota sine of 80 into sine of 80, and we can just multiply e exponent minus 6 to on with both of them, so it becomes x naught e exponent minus 60 cos of 80 plus v naught plus 6 x naught divided by 8 e exponent minus 60 sine of 8 of t. So this is the total solution of our that mass spring damper system, which has a multiple springs and the damper with the initial condition that is. So this is the method using this is the solution using the general solution method. Now what we can do is we can try the same solution using the Laplace transformation. So I'm not going to repeat all the steps because we know what the differential equation we have here, so we can just directly jump onto that now using Laplace transformation. So we know we had the equation of motion for this system equals to mx double dot plus b1 plus b2 x dot plus k1 plus k2 x equals to 0, and we know the initial condition, the final condition. So now we are going to take the Laplace transformation for this one, and since this is double derivative, this is single derivative, that's a linear value, so we will have the Laplace transformation for first one, let's say m, and Laplace transformation of x double dot plus b1 plus b2 into the Laplace transformation of x dot plus k1 plus k2 into the Laplace transformation of x. It's better to write them as x of t so that you can differentiate between them. I'll just rewrite this one: Laplace transformation of x double dot of t plus b1 plus b2 into the Laplace transformation of x dot of t. So we represent Laplace transformation by a curly bracket plus k1 plus k2 into the Laplace transformation of x of t whole equals to 0. So if you take the Laplace transform double derivative, we have seen in the properties in this lecture in the beginning, so it will become s square x of s minus s into initial condition of displacement minus velocity initial condition at times t is equal to 0 plus b1 plus b2, that remains same, and then this becomes equal to s x of s minus initial condition plus k1 plus k2 into that is directly transformed into Laplace domain. So this is what you have at the end, and now you can substitute the values of initial condition in the bound here. So it becomes ms square x of s minus x at 0 is x naught minus x naught minus v naught. Let's keep it like this one at the moment, plus b1 plus b2 s x of s and minus x naught, that's the initial condition, plus k1 plus k2 into x of s equals to 0. Now you can simplify your, open up all the brackets and simplify your equation. That's simply algebraic operation. So you will have at the end as x of s equals to ms square plus b1 plus b2 s plus k1 plus k2 equals to ms x naught plus mv naught plus, I just open up the bracket, I'm writing it directly, it's a simple algebraic operations, b1 plus b2 x dot. Now what you can do is you can use those values of m1 m2 b1 b2 all of these which we saw in the beginning. I'll just plot those values in this equation, and we will have x of s into, it becomes 10 s square plus b1 plus b2 is 120 s plus k1 plus k2 is 1000 equals to ms, that is 100, 10 s x naught plus 10 v naught plus 120 x naught. And so what you can do is you can keep x of s here and just 10 s x naught plus 10 v naught plus 120 x naught, and in the denominator you will have 10 s square plus 120 s plus 1000. So this is what you have. Now here comes another step. This is mostly used in, which you will have to use in your Laplace transformation method, and that is partial fraction. So I hope you remember this one. If you want, I can record another separate lecture to recall what the partial fraction is, how you can decompose this rational function into the simple fraction. So this is what the partial fraction does. It decomposes a rational function into the simple fractions. So what we are going to do is we are going to arrange it in such a way that we can use a simple fraction, because now we have the final solution of the Laplace transformation. What we have to do is we have to do another thing called the inverse Laplace transform to convert it back into the time domain and just check out our answer, does it matches the general solution method or not. So we just simplify it further. Before going to that, just take 10 common out of all of these, so it becomes s x naught plus v naught plus 12 x naught divided by s square plus 12s plus 100. So I have just reduce it further. If you check out this lower one, you can divide this into simple fraction like s x naught plus v naught plus 12 x naught whole divided by, it can becomes s square plus 12s, and you can divide the 100 into 36 plus 64. It's also 100, so it becomes s x naught plus v naught plus 12 x naught divided by, this become s plus s square, and that is 8 square, is it? So we just use a simple simple fraction of this complex polynomial equation. So now that is we have s plus 6 square plus 8 square, And you can do the simplification on the numerator as well. So it becomes x of s equals to s x naught plus 6 x naught. You can just divide this 12 into 6 and 6 plus 6 x naught plus v naught and divide by s plus 6 square plus 8 square. And we can just take x naught as common to become s plus 6 and plus 6x naught plus v naught, and the denominator is same. I'm not going to write it again, just to keep it simple. Now you can write separately under each x term and the numerator. So it becomes x into s plus 6 into s plus 6 square plus 8 square plus 6 x naught plus v naught divided by 6 s plus 6 square plus 8 square. Now what we are going to do is we are going to take the Laplace transform for this function, but before that we have to simplify it even further. What we can do is look, okay, what we are trying to do, we are trying to doing the inverse Laplace transform of our function x of s, so that we can go back to the time domain. And if you refer back to your table that I show you in the beginning, I will share that table with you. So in this table you have a time domain function and the Laplace transform function of that one. So currently what we are doing is we are already in the Laplace domain, so we are trying to go back into the time domain. So what I'm trying to do is I'm trying to arrange all my fractions in such a way that it matches any of these or the combination of these, so that I can directly transform that back into the known corresponding time domain function. So if I manage to arrange my those fraction, let's say in this form, I know that's the inverse Laplace transform, it will be sine omega t. If I manage to arrange themselves in this form, I know that the inverse Laplace transform should be equal to 1 over a into 1 minus e exponent minus at. So this is what we try to do in the inverse Laplace transform. Use a partial fraction, try to arrange everything to match any of these in this column, and let's do the inverse Laplace transform and get the time domain function directly. So this is what we are trying to do here. So what we can do is currently I'm not doing the inverse Laplace, just simplify. You can further play with the second one so that to matches any of those ones. If you see there's a pattern here, x plus 6, s plus 6 divided by s plus 6 square plus 8 square, it matches some of those. I will show you. So it becomes, that's x naught, it becomes x naught into s plus 6, just leave it like this, square plus 8 square plus, maybe we can multiply divide this by 8, so it becomes 6x naught plus v naught divided by 8 into 8 divided by s plus 6 square plus 8 square. Now I can take the inverse Laplace transformation of this one, and if you see it is, let's say I call s plus 6 equals to, just for your understanding, let's call it a. So this expression is becomes x naught into a divided by a square plus 8 square, and here 6 x naught plus v naught divided by 8 is equals to 8, sorry, into 8 into a square plus 8 square. So if you just matches this one with our table, so one is s divided by s square plus omega square, one is corresponding to omega divided by s square plus omega square. So I know if I take the inverse Laplace transform of first expression, it will convert cosine, and if I take the inverse Laplace transform of the second expression, it becomes to the sine. Correspondingly, just maintain the position of each variable. So if we take the Laplace transformation of this one, so this will become, again, convert to x of t. It's an inverse Laplace transformation. X naught will remain at its place. We are applying the inverse Laplace transform on this expression, so it will become e exponent minus 6t because that is not just a, that's 6 s plus 6 into cosine of 8 of t plus 6x naught v naught plus v naught divided by 8 into e exponent minus 6 of t into sine of 8 of t. And if you just recall that one, well, that's a combination of this one. Yeah, like this one. So we had two different, first expression was this one, s plus a divided by s plus a square plus omega squared becomes e exponent minus 80 cos omega t. Second expression was omega divided by s plus a square plus omega square. It becomes turned to e exponent minus 80 sine omega t. So this is what we have at the end as x naught e exponent minus omega t x plus 6. So this is what we have using this function, and it should match with the time domain function. So you see x naught e exponent minus 60 cos 80 and this one, and plus 6x naught plus v naught divided by 8 into e exponent minus 60 into sine 80, and we have the same one. So you see this is the length of the solution using the Laplace transformation, and this is the comparatively much longer length using the differential equation method. And given just keep in mind, I didn't show the solution of this, I just directly write the steps. So even if you follow those steps, it will become even longer. And you must have noticed that we didn't had to incorporate the initial condition separately. It was part of the Laplace transformation, so it saves a lot of steps. Only thing is you have to play with this partial fraction to get your final solution. So I hope this was a good demonstration of the Laplace transformation, its physical intuition, how it helps you to study the vibrating system, and how it is in comparison with the general solution method or time domain methods. Laplace is a frequency domain method. So that's all for this lecture. I will also upload some solve example using the Laplace transformation and some practice problems. So I hope you enjoyed this lecture. Just let me know if you have any question. You can drop me an email or contact me on my personal number. See you inshallah next week. Assalamu alaikum.